today I'm going to talk about finding stars about to die. And this background image you can see is the Crab Nebula, which is the object that on the sky I like the most. One, it's very magnificent looking, stunning look, right? And second is more of an academic reason. It's, as we know it, the origin is a death of a massive star that blew up 1,000 years ago, about 1,000 years ago. Massive star, about 10 times the mass, heavier than our sun, blew up and created this. So what are interesting about these? So as a person working on supernovae, one of the main things I try to answer is how do massive stars die? And this is basically connecting the dots to seeing to the massive stars that we see and the things like Crab Nebula that we also see, and trying to connect the dots to understand how these massive stars came into these beautiful images that we see. And my parents back in Tokyo sometimes ask me what I work on, and I always tell them I blow up stars for a living. And it's not that I actually go to one of these stars and blow them up. It's that I try to understand using the laws of physics as a physicist to try to connect how these stars go into these explosions. And this is not only me that's doing it. This is like generations of astronomers and physicists' efforts to try to connect these. And today I'm going to talk about, using this 15 minutes, what we know about these massive stars and their explosions and what we don't know yet. Okay, so inside a massive star, you've seen images like these. One example is like Betelgeuse, which is about 15 times heavier than our sun. And these stars have a structure. It's very compact in the inside, hot in the inside, cool on the outside. And I can think of an analogy here. So if you drive in central LA, if you drive in the freeway, it's very fast cars, lots of cars, and sometimes you see cars crashing, which I hope none of you were involved in this, but you sometimes see this. And this exact same thing is happening in stars. And it's not cars, it's hydrogen atoms. So inside a massive star, the central, dense, hot regions are able to form an environment where the two hydrogen atoms collide. And in physics, we call this nuclear fusion. And this leads to the production of helium. So one step further in the periodic table. And what if you turn all the hydrogen into helium? Then another nuclear fusion happens where you form helium into carbon. And this process goes on inside the star. And you eventually end up in this shell structure or onion shell structure layer where heavier atoms of the iron are formed as you go inside. So it's hydrogen, helium, carbon, neon, oxygen, silicon, and iron. And what chemistry tells us, or physics as well, is that you can't burn further than iron. Iron is the most stable element in the universe, in the periodic table. So what happens is that you can't fuse iron anymore. So the star can't get the nuclear energy out of it to support it. And the inner part of the star will gravitationally collapse. And it gets denser, gets hotter. And what we think is that it triggers an explosion where the central core is left behind with the outside exploding. And what we believe this is a supernova. So the star blowing up by this is what we believe we see as a supernova. And And these supernovae are very bright explosions. They can become almost as bright as a galaxy. So you actually see these a lot when you look at the night sky. And you can't see it with your naked eye most of the time, but with telescopes you can. And this is how people have found them. So early days it was a naked eye. Early 1900s it was the photographic plates. Now it's a bunch of robotic telescopes around the world that is finding all these supernovae. So we kind of know these exist, and these are quite important for us because these stars that have formed up to silicon, like all these heavier elements like carbon and oxygen, because they blow up, they bring all these elements into interstellar space. And these carbon, oxygen, iron, silicon, these elements are very important for us. Water is H2O. Like, we have carbon dioxide, right? So understanding these is more or less related to understanding us. So we want to go a step further. So we know that the star can explode. But let's go one step further. So can we actually see these stars about to explode with all these heavy elements formed inside? The question is, it's quite hard. One reason is that we only see the star's surface, right? So it's the same for our sun as well. Like, we only see the sun's surface, and we have no access to what is inside by light. So whatever is happening inside the star, it's really hard to see. So we have relied on theory or the laws of physics to try to understand what's inside. The prediction is that the stars look pretty much the same over the final million years. So once these helium cores have finished forming, these stars basically look like these orange little big blobs. And it'll look the same, even if you form a bunch of elements inside. That was the standard paradigm. But recently, nature hasn't been so kind, and we've been finding that this is not always the case. So we look at supernovae. This is the only plot I'm going to show in this talk. But this is what astronomers use called a light curve. This is basically showing the brightness of any kind of object as a function of time. So a supernova is as bright as a galaxy over a few months. And we actually see a lot of these supernova explosions that are colored dots right here. And the shaded region right here is what we believe massive stars shine as. So it's not that bright compared to a supernova. So the standard paradigm was that you would be around where the massive star is, where the shaded band is, and then you suddenly blow up a star, so the light curve or the points shoot up. What people have found recently is a different picture. These are way brighter than normal massive stars. This means that there's some energetic unknown things happening in the final months of the millions of years of a massive star's life. And we don't really know what the mechanism of this yet. It might be some intense nuclear fusion happening in the center of the star, and it's happening on the final months of the star's life that is triggering this very energetic outbursts. It might be due to some extreme object nearby, like a black hole stripping up material from the star and shining it. This will be solved, hopefully, by the near future Rubin Observatory. So Rubin Observatory has started taking these images. They are also fascinating images. But they can search for these supernova or things that get brightened suddenly. And the way they do is like how many other supernova searches have been done, where you take a picture of an object and come back to the same place later, like a week later, take another picture, then you see something different, and that is a stellar explosion. And Rubin can not just only do this, but can do this in an unprecedented sensitivity. They can do it 100 times deeper than previous surveys of this kind have done. Which means that not only can Rubin find lots of supernovae, they can find lots of stellar activity outbursts going on in the final months that we just seen before. So that's the take-home message. So massive stars make supernovae. They make all of us. It's really important part of our universe. But the final moments before the supernovae is still an open question. It's a mystery. And we hope that Rubin Observatory will find lots of these pre-supernova brightening to tell us how the massive stars behave in the final moments of their lives. That's all. Thank you.